Welcome to BC Gnomonics. In this video, we're going to be examining a portable equatorial sundial. Now, there are three main steps that must be taken to properly set up and orient this dial. The first being ensuring that the gnomon assembly is oriented perpendicular to the dial plane. As we can see here, this is done on this dial by flipping this small metal tab over the gnomon assembly bar. The second step is setting the dial for latitude. As you can see here, there's a latitude scale with numbers from 90 to roughly 25, although the dial can be set for latitudes lower than 25. You just kind of have to estimate on this specific model. Now, if you're using the dial at the equator, you would set it to 0 and it would look something like this. If you're using it at the North Pole, you would set it to 90 and it would look like this. My latitude is 44 degrees, so I'm going to set it right about here. Now, the final step with any azimuth dial is aligning true north. As you can see here, this dial has an embedded compass, and what you may notice is that this compass is slightly offset. You might expect north to be up here, and that is because a previous owner has corrected it for magnetic declination. Now, what that is the difference between magnetic north and true north. And that's a value that differs with geographic location and across time. So if you would like to know your magnetic declination, you can look it up on the internet or consult some sort of almanac. But for the purposes of this demonstration, I'll be assuming that this correction is the valid magnetic declination for my location, although I have no idea if that's the case. I have not measured this particular dial, and it's likely slightly off. But for demonstration purposes, this will do just fine. So once we orient once we orient the needle north, the dial as a whole will point to the North Star. This gnomon will point parallel to the Earth's axis of rotation, pointing to the North Star just above the northern end of the axis, and the dial plate here will parallel the Earth's equator. And so this dial, as it's set up now, becomes a model of the Earth at this exact location. So as you can see here, at the equinox, the sun's path exactly parallels the equator, which on the dial is this path right here. So that at the equinox, the sun travels along here with the shadow traveling the opposite way as the sun moves. So as the sun moves along the equator, the shadow moves along the hour scale. Now during the summer solstice, this path is translated north. So the sun would move in an arc like this, and the shadow would likewise move opposite the sun. Now, at the winter solstice, the arc is slightly south of the equator, and so it would take this path. Now, on some dials, there's a solid disk for a dial plane, and in those cases, you can't read the time on the same face at every point of the year. In those cases, you would need a separate dial face and gnomon on the bottom side of the dial. And I will model that just for demonstration purposes. As you can see, this dial is now a solid face equatorial. And during the winter months, the sun would travel along an arc this way and would not cast a shadow on this top face. So in those months, you would rely on the lower face, which also has numbers, and an extended gnomon. So let's take a look at this dial as it might be used at the North Pole, just for demonstration purposes. So as I said before, if used at the North Pole, this dial would be oriented like this, with the gnomon paralleling the Earth's rotational axis which goes right through the zenith if you're at the exact North Pole. And that can be seen right here in this diagram. So one thing you might be noticing is that the path of the sun for the winter solstice is absent from this diagram. And that's because during the winter solstice, the sun is completely below the horizon. So the path of the sun would be a circle down here below the local horizon, and as such could not be seen on the sundial. During the summer solstice, however, the sun is fully above the horizon, as opposed to the summer solstice at our latitude, which rises and sets. This one neither rises nor sets and travels in a circle, which would mean that throughout the course of the day, you would be able to see the shadow travel in a complete circle over all 24 hours of this dial. Now, one final example is the dial's use at the equator. And as you can see on this diagram, at the equator, if you're on the exact equator at 0 degrees latitude, the sun at the equinox will travel in a perfect 90-degree arc through the zenith. That's the point directly above the observer. And this is the only point when the sun will pass through the zenith, is at the equator, at the equinoxes. During the summer and winter solstices, the sun will travel also in a 90-degree arc, although north or south of that equinox path. So that will conclude this demonstration. Please let me know if you have any ideas for other instruments you'd like me to demonstrate, or other concepts you'd like me to demonstrate with instruments that I've already highlighted. If you're watching this on YouTube, feel free to leave that in the comments, or if you're watching this on bcgnomonics.com, feel free to submit a contact form with any suggestions you might have. Thank you for watching.